the last part of this notes packet is naming ionic compounds that contain polyatomic ions. So it's the same thing that we just did on the last page, but now it's going to be a combination of predictable valence electron metals as well as transition metals. So if I start with this first one, I skipped over these and we'll come back to that in just a second. If I look at this first thing, what tells you that you're using polyatomic ions is that you have this whole clump of nonmetals at the end. It's not just monatomic, meaning I have one metal and one nonmetal. I have a bunch of elements together. At this point in time, we haven't learned covalent compounds. So when you look at something that has a whole bunch of different elements, you're going to immediately search your periodic table or search your polyatomic ions chart for what polyatomic ion is present in that compound. So if I look at this first one, you should recognize sodium because we use it all the time. So sodium is your metal in this case. And then this whole thing right here, C2H3O2, doesn't look like something that we've used before. So start with your polyatomic ions chart and see if you can find that one. It looks like most of you have found it. So when you look at sodium, since sodium is in a group that has predictable valence electrons and we know its oxidation number is +1, we do not need to include a Roman numeral in its name. So we would just name this as sodium and then the name of the polyatomic ion, which is this first one called acetate. So when I name this, the sodium acetate is the correct answer. The second example we have here is calcium bonded to this polyatomic ion. Since calcium is also in a group that has predictable valence electrons and therefore a predictable oxidation number, we know that calcium is going to have a +2 charge, so we don't need to include a Roman numeral in its name. Then I would look up this polyatomic ion, ClO3, and there's a whole bunch of ClOs on here. So ClO3 is called chlorate. Make sure you're looking at the right one. And so I would just name this calcium chlorate. Where it becomes a little bit more difficult is when you have a transition metal bonded to a polyatomic ion. I know that this is a transition metal because when I look up CO, cobalt, on my periodic table, it's in the D block. So if I zoom this out so you can see where it is. When we label our valence electrons and our oxidation numbers, we're only labeling our tall groups. And cobalt is in this middle group that we skip labeling. So on your periodic table, you should have written on here that we use Roman numerals to describe the oxidation number of any of these. What they have in common is they are all positive, and we use Roman numerals. I'm going to abbreviate that as RN. I know I have another periodic table somewhere where I wrote it out. So we're going to use Roman numerals for your entire D block. If you weren't here this day, make sure that you write this on your periodic table so that you don't forget. So you're going to use Roman numerals for the entire D block, the entire short section, as well as two other specific elements, which are tin and lead. Those are both in group 14. So the day that we did this in class, we went through and actually changed this from, instead of saying ±4, we changed it to a question mark for the oxidation numbers. That way you remember you need to use Roman numerals for this group and that group to describe their oxidation numbers. So if I'm looking at CO and OH2, we have to basically do the reverse crisscross to figure out what the oxidation number would have been for cobalt. So when I'm looking at this, if I don't know what cobalt's oxidation number is, I'm going to put it as just CO with a positive question mark because I know that it's positive and that's it. And then if I have OH and then a 2 on the outside of the parentheses, that tells me I have 2 of them, but what is OH? Perfect. So if I look up hydroxide on my polyatomic ions chart, OH with a -1 charge is called hydroxide. So when these crisscross, I know that that 1 would tell me I need 1 cobalt, which is what I see in my formula. So then this question mark would have been whatever crisscrossed down to hydroxide. So that in my formula is a 2. So based on what I see in the formula, this tells me that my cobalt would have started with what charge?
2.
2, a positive 2. So this would just be called cobalt, and then in parentheses, 2, I have to include that for the name to be correct, and then hydroxide. If you don't include the Roman numeral 2, then your name is incomplete, because if you just see cobalt hydroxide with no 2, there's no way for you to write the formula from that name. So it has to be included. And then I think with that example, we can go back to the description of this, or the instructions. So this example here that has copper and nitrate, it did the same thing. So if I have copper and nitrate, I would need to look up nitrate first and figure out what its charge is. Nitrate, according to my polyatomic ions chart, has a -1 charge, and since that does match what's down here, then you can trust that this is the actual oxidation number of copper. So since I know that copper in this case would have a charge of +2, I would call this copper 2 nitrate in my example. I'm looking for an example on this one that has one that doesn't match. I'm actually going to flip over. If you go to the back page, there are some cases where it won't necessarily match. That kind of describe why you would look at the anion first instead of just using the subscript every single time. So if I go to number 27, what's that here? On number 27, I have cobalt again, so that's the same element that we just looked up. So you can call it cobalt, since we know that that's what our metal is. I also know that it's a transition metal, so it's going to need Roman numerals, so I'm going to put Roman numeral parentheses there. And then that second part, this PO4, is a polyatomic ion that is called phosphate. So the name is going to be cobalt something phosphate. But we have to work backwards to figure out what cobalt's oxidation number actually is. So in this case, if I look up phosphate, not just the formula, but the oxidation number, it has a charge of -3. So I know that when this compound was formed, phosphate had a -3 charge that should have been crisscrossed down. If the compound is given to you, you can trust that it's been crisscrossed correctly. So if it's not showing up, it's not because of a mistake. The only reason that this oxidation number wouldn't match with what's right here is if it's been reduced. So the fact that that 3 doesn't show up in the formula as a subscript on cobalt tells me it's been reduced. So I know I started with PO4 with a -3 charge. I also know I started with cobalt with a plus something charge. I know that the 3 got crisscrossed down and had to start as the subscript here, but the reason it's not showing up in my formula is because it's been reduced with whatever the other charge was. If you get lost or confused there, my advice is to just use guess and check. Your oxidation number, at least for the purposes of this class, will always either be 1, 2, 3, or 4. If it's reducing with a 3, then I think 3 is a good place to start your guess. So if I say that this is a 3, and I had a subscript of 3 and another subscript of 3, they would both reduce down to just be CO and then PO4. So that is what happened, and that tells us that this would be cobalt with a +3 charge, and therefore I would put a Roman numeral 3 here. So you basically have to work backwards anytime you have a transition metal to figure out what its charge would have been. Don't just trust the subscripts because they're not always going to show up. There's no 3 in this entire formula, so there's no way that we would have known that without going through the background work of figuring out what the charge had to be and which one had to show up and cancel with it. All right, for the rest of them on the bottom of page 3, you're really just breaking it down into the cation and the anion. So in most cases, it's going to be a metal and then a polyatomic ion. Here we have radium hydroxide. Radium is Ra. And according to your periodic table, what is the charge for radium?
2.
Plus 2. And then hydroxide is OH with a -1 charge. So when you crisscross it, this tells me I need 1 radium and 2 hydroxides, so it would be Ra. And then it's still important that you put OH in parentheses and a 2 on the outside of the parentheses. If you don't do that, let's see if I can put this up here. If you just put Ra and then OH2, the difference is that this shows me that you have 2 hydrogen atoms and this shows me that you have 2 hydroxides. So when you crisscross it, you need to make sure that you put the entire polyatomic in parentheses so that the 2 applies to everything in those parentheses. Then we have magnesium acetate. Magnesium is Mg with what charge?
2.
Also a +2. And then acetate is the long one, C2H3O2. I was pointing up here. Just because the line is so short, I'm not going to write it out there, but I will right here. So Mg. That 2 would crisscross on the outside of that entire formula for acetate. So I need to put acetate in parentheses, C2H3O2, and then the 2 on the outside. Acetate has a -1 charge that crisscrosses down to magnesium, so that's why there is no subscript there. Sodium peroxide is kind of a special case where sodium has a +1 charge, according to our periodic table, and then peroxide is a polyatomic ion that's O2 with a -2 charge. So when you crisscross this, that 2 becomes the subscript for sodium, and this 1 just won't show up on peroxide. So when you write it, it becomes Na2O2, which if you've been practicing, you might have the urge to reduce that. However, because peroxide is a polyatomic ion, we're not going to reduce it, because if I divide this whole thing by 2, I no longer have peroxide. So that is basically part of its name. That 2 is going to stay there. So even though this might look improper, it's correct because peroxide will keep that 2. So that one's just a little bit special. Ammonium phosphate. Ammonium is NH4 with a +1 charge, and phosphate is PO4 with a -3 charge. So crisscrossing them, I would need 3 ammoniums. So that would end up going in parentheses, and the 1 would come down to phosphate. So NH4 in parentheses, and then PO4. Mercury to acetate. So mercury is Hg. It has a +2 charge. You don't even have to look at your periodic table because this 2 is where I got that from. And then acetate is C2H3O2 with a -1 charge. This 2 would tell me I need 2 of these, so that has to go in parentheses. And this 1 just won't show up in the formula. So Hg, and then open parentheses, C2H3O2. And a 2 on the outside. So these 2 formulas look really similar because this is a metal with a +2 charge and this is a metal with a +2 charge. And then silver nitrate is our last one. Silver is Ag. You don't even have to look at the periodic table for its charge. Since it's a transition metal, its charge is given as a Roman numeral, so it's a +1. And then nitrate is NO3 with a -1 charge. When you crisscross it, you aren't going to have any additional subscripts, and it becomes AgNO3. And that's it.